Okay, so what we want to do now is discuss the relationship between three concepts that we've encountered and built this kind of a picture, of a diagram that summarizes all these notions in terms of what implies what and what doesn't imply what. So the first theorem in that direction is going to be the theorem that if f is differentiable at a certain point, then f is continuous at that point. Okay, differentiability implies continuity. Let's prove this. I don't know if you remember the single variable proof of this same statement, but it's going to be very, very similar. It's going to resemble it a lot. So what do I want to calculate? I want to calculate the limit as hk goes to 0, 0 of f at x0 plus h y0 plus k minus f at x0 y0. This limit, I want to show that this limit is 0. If I show that this limit is 0, then by limit arithmetics, this is just a fixed number, right? If this limit is 0, then by limit arithmetics, the limit of this thing is just f at x0, y0. And that's the definition of continuity. Do you agree? Okay, so let's do that. So this limit by star is the property from the definition of differentiability. That's what I know about the function now. This limit I can rewrite as limit hk goes to 0, 0 of, and now I'm going to replace this by a times h plus b times k plus alpha of h k times the root of h squared plus k squared. This is star. Do you agree? That's the definition of differentiability. This equals this, where alpha of hk goes to 0. Do you agree? Now, as hk goes to 0, 0, a is just a number. We know it's the partial derivative, but it's just a number. H goes to 0. So this thing goes to 0. Do you agree? Likewise, b is a number. K goes to 0, so this component goes to 0. Alpha of hk goes to 0, also by the definition of differentiability, and the root of h squared plus k squared goes to 0 as h and k both approach 0. Do you agree? So the limit of the entire thing is 0. Good? So therefore, if the limit of this difference is 0, then just this tends to this, and that's the definition. Let's write that. So conclusion, the limit as hk goes to 0, 0 of f at x0 plus h, y0 plus k equals, I can move this by, I can add fx0, y0 to both sides. It's a constant, so it just equals this. Okay, you can rewrite this if you want. Instead of x0 plus h, just write x, and instead of y0 plus k, just write y, and then instead of hk goes to 0, 0, write x goes to x0 and y goes to y0. That's the definition of continuity. Do you agree? Everybody? Okay, so this completes this proof. So every differentiable function, this property is the right property, at least in this sense. Okay, it does do exactly the same thing the differentiable for single variable function guarantees continuity. Okay? Okay, here's another theorem. Another theorem. This other theorem is, the proof is not easy. It's more complicated. It calls for there's a Lagrange argument there, and it's not a trivial proof. We're not going to prove it. We're just going to state it. And the theorem says that if f has continuous partial derivatives at a neighborhood of x0, y0, then f is differentiable at x0, y0. Okay? Partial derivatives, remember that the partial derivative, for example, the derivative of f with respect to x, the way I obtain it is by freezing y, right? But what I get is a function of two variables, right? df to dx is a function of x and y. For every x and y, I get a different number. Do you agree? So df to dx is a function of x and y. df to dy is a function of x and y. Those are both two variable functions. And I can ask for them to be continuous in the sense of Calc 2 as two variable functions in a neighborhood of x0, y0. That's requiring more. Okay, that's saying that both partials are continuous in a neighborhood of the point. And if that happens, that implies differentiability at the point. Okay? And we're going to have a name for a function that has continuous partial derivatives. Okay? Functions that have, we are going to denote, we will denote functions with continuous partials by, we're going to say that f belongs to C1. Okay? C1 means it has continuous partial derivatives. Okay? By the way, C2 later is going to mean that it has continuous partial derivatives of order 2. Okay? We'll discuss that later. Okay? So the picture that we have, this is the diagram that I mentioned. Okay? Again, I'm not proving this theorem. The diagram that we have is the following. Here we have functions that are C1 near the point x0. So let's maybe make this slightly bigger. Near the point x0, y0. This can be weakened a bit. You can require for it to be you can require it to have partials at a neighborhood and only require them to be continuous at the point. But we're going to just say this. This implies that f is differentiable. Whenever I don't write anything else, I just mean at the point x0, y0. At the point x0, y0. And this in turn implies that f is continuous at the point that we just proved. Do you agree? And this also implies, being differentiable also implies that f has partial derivatives. Because if it's differentiable, we proved that the a and the b are the partials, right? So existence of partials. Do you agree? So this is the diagram that we have so far. Okay, we proved this and this, we just stated without proof this. Okay? All the other directions, any arrow that does not appear here, well, except composition of arrows, right? If f is C1, then it's differentiable, then it's continuous. So clearly if f is C1, then it's continuous. That's not a very bright thing. But any other implication that might be hidden here is false. Okay? So it's not true that a continuous function necessarily has partials. This is false. And it's not true that if a function has partials, then it's continuous. This is also false. And it's not true that any continuous function is differentiable. This is also false. This was false in Calc 1. And it's not true that being differentiable implies having partials which are continuous in a neighborhood. So all the other directions here are false, and we've seen some examples. So for example, we've seen, let me mention here some examples. We've seen this function, seen and discussed, the function f of xy equals xy over x squared plus y squared. That's when we're not at the origin, and 0 at the origin. This function, we proved, had partial derivatives at the origin, but was not continuous. Okay? So this function is a counterexample to what would be a theorem, were it true, that having partial derivatives implies continuity. So this function is a counterexample and proves that this is not a theorem. Okay? Since it's not continuous, it's clearly not differentiable. That can be proven by definition, but it follows from the theorem. So this function is also a counterexample to one arrow that I forgot to write, and this is this arrow. This is also false. And this is a counterexample to this arrow as well. It has partials at 0, but it's not differentiable. Clear? Now, coming up with a counterexample for a function that is continuous but not differentiable should be easy. Yeah, very good, very good. Somebody was doing there, you can't see it, but somebody was doing this. Right? Even in Calc 1, if you take the absolute value function, f of x equals absolute value of x, at 0 it's continuous, but it's not differentiable. Do you agree? So how would you generate from that a two-variable function that is continuous but not differentiable? You can just take it and smear it along the y-axis. Okay, take something that looks like this. Can you understand what I'm trying to draw? So just take the function f of xy equals the absolute value of x for any y. Okay, so at any y you look, you get this v-shaped thing. Do you agree? So this function, whenever x is 0, independent of y, it's going to be continuous at that point, but it's not going to be differentiable. It's going to have a cusp there. Do you agree? Okay? Again, one can prove that by definition, but it's really easy to see. For example, a very easy way to prove it is that it doesn't have the partial with respect to x, because the partial with respect to x is precisely trying to differentiate the absolute value of x. Do you agree? So this is going to be a counterexample for both this thing, a function that is continuous but doesn't have partials, and a counterexample for a function that is continuous but is not differentiable. Were it differentiable, it would have partials. That we proved. Clear? So the only counterexample that we're missing is how does a function that is differentiable but not C1 in a neighborhood, doesn't have continuous partial derivatives in a neighborhood? And I'm going to write for you an example like that. So, and I'm going to leave it to you to verify it. It takes a bit of work. Okay, it takes a bit of work. You have to calculate the partial derivatives, show that they're continuous functions at the point is going to be 0, 0, but then argue that the function is differentiable. Show that they're not continuous, the partials, but then argue that the function is differentiable. Okay? Even in Calc 1, finding functions which are differentiable, but their derivative is not continuous, was a bit of a challenge. Those were functions which are kind of pathological. Did you see functions like that in Calc 1? Okay, functions which are differentiable, but the derivative is not continuous. Okay, so you need to look at things like maybe, I don't know, x to the 3/2 times sine of 1 over x, or things like that. Okay, I don't know if you did that in Calc 1, but this is a Calc 1 phenomenon, just at a point, not at x0, y0, but at x0. And it's the same idea here, but it's always kind of pathological. It's not really pathological. It's pathological in the sense of the functions we're used to seeing. Okay? So here's an example. Look, for example, at x squared plus y squared times sine of 1 over the root of x squared plus y squared. And 0 at 0. Okay? And its single variable counterpart would do the work for a single variable function as well. So this is a counterexample for this. You can verify it. I'm not going to do all the calculations. But there's a point to why I'm writing something somewhat scary and not exactly natural like this, and why I'm saying that it's, in a sense, pathological, in a sense. And the reason is the following. Checking differentiability is sometimes, in general, not trivial, not easy. We saw an example where we checked differentiability in the previous episode, and we saw that it requires some work, right? You have to find the alpha and show that it goes to 0 as h and k go to 0. It requires some work. Checking that a function has partials and that the partials are continuous is in many, many cases really easy, especially if everything is elementary. Okay, if it's an elementary function, taking the derivatives is easy, the partials, and saying that they're continuous is kind of a trivial observation, and this could be very easy. Okay? So what we're going to do from now on in this course is throw away this box. In what sense? Well, all the functions that we're going to look at are going to be one of two possibilities. Either they're going to be very nice and smooth in the sense that they're C1. And if they're C1, we know they're differentiable and we know everything holds. And if they're not going to be nice and smooth, if they're going to have some singularity, some cusp or some discontinuity or something like that, then they're not even going to be differentiable. So we're not going to look at those annoying functions in between that are differentiable but are not C1 in a neighborhood. Okay? So all our theorems are going to start with let f be C1 in a neighborhood. All our theorems, although sometimes you can prove the theorems for functions which are not C1 in a neighborhood but only differentiable. Okay? Is it clear what's going to happen? And this is just to make life easier. Okay, we're going to say, okay, we're engineers. We're not mathematicians. Mathematicians love the functions in between. That's what they crave. That's what they want. The functions that are tricky. This, but not this. Okay? But we're from real life. We're engineers. We're going to say, okay, it's either good or it's bad. It's not annoying in between. Okay? So what I'm going to do is the idea clear? Well, one more thing before I actually do it, before I remove differentiability altogether, there's another theorem. There's another theorem, which we didn't state yet because we didn't define yet. And that theorem is that differentiable, if and only if, we mentioned it, but we didn't write it yet, if and only if f has the tangent plane. Just like in Calc 1, having a tangent line was equivalent to being differentiable. So, and it's clearly not equivalent to having partials. It implies having partials, but it's not equivalent to having partials. Okay? So I do want to define what a tangent plane is, and then this theorem we're not going to prove. Okay. By the way, one way of defining a tangent plane, remember we had the candidate for the tangent plane? Okay. So one way of defining is saying that if f is differentiable, and then this is a non-theorem. Okay. But there are other ways of defining it that make more sense geometrically. Okay. So what I'm going to do now, and I'm going to write it and then do it. So let's first write it and then do it. In this course, we will consider functions. We will only consider functions that are either C1 in a neighborhood. Those would be the good functions, and all the theorems would be on functions which are C1. Most of the theorems we're going to see in various contexts are going to start with the words, let f be C1 in a neighborhood. Okay? Or not differentiable. Okay? And we're not going to consider those functions which are not C1 in a neighborhood, but are differentiable, and therefore we're going to ignore that, that in-between square. Clear? Okay. So what that implies in terms of the drawing is that we're just going to unite these two. So I'm going to erase this now. And I'm going to erase this altogether. And now we're going to have functions which are C1, which are going to imply being continuous. Ah, this is fun. Okay, so being C1 implies continuity, and being C1 implies having partials. And this thing still exists, but again, it's just an implication now. Having a tangent plane is equivalent to that in-between square that we just ignored. Is it clear what just happened here? Okay, I just took away this mathematician sort of phenomenon, and we're going to focus on functions which are more standard in a sense. Yes?
Is the tangent plane a single-sided arrow now?
Yeah, because we know that it's equivalent to being differentiable, but differentiable does not imply being C1. Okay, so I can't say that it's a two-directional arrow, that it's an if and only if statement any longer. Okay, it's having a tangent plane is a bit weaker. That example that I had up here and I just erased has a tangent plane because it's differentiable, but it's not C1. That's the... Okay, clear? By the way, note that I emphasize C1 in a neighborhood. Okay, it's not enough to being C1 at a point. Okay? Okay, so the last thing I want to do for now is define what the tangent plane is, okay, and state some facts regarding. So let's do that. At this point, I can erase the definition of differentiability that we had. Okay, so definition, we say that a plane P is tangent to, and we're going to regard it as, in this discussion, we're looking for planes which are tangent to graphs of functions, right? But in general, a plane can be tangent to any surface. It doesn't necessarily have to be a graph of a function, okay? So is tangent to a surface S at the point P0, so this is big P for plane and P0 for this little point, if it satisfies two things. One, P0 is contained in P, so P goes through P0. And by the way, P0 originally has to be a point in S. Let's add this. Okay, so they have to be touching at that point. So that's the easy property. And the other property is that if you take any point on the surface, any general point on the surface, and attach it with a secant, with a chord to the point P0, the angle between that and the plane is going to go to 0 as the point approaches P0. Can you picture that? Here's the surface, my head. Here's the point where we want to find the tangent plane. Tangent plane, okay? Take any other point here. This is P0, right? Take any other point here, attach it with a chord. It's going to go straight through my head. Ready? Ouch. Attach it with a chord. It forms an angle with the plane. Do you see the angle? Okay. As I take points closer and closer to P0, that angle has to approach 0. Do you see? Clear? The geometry clear? That's the definition. So 2, for any point little p in S, the angle between P0, this is the vector, and the plane P, well, it's not for any point. Okay, this is not phrased really well, but never mind. The angle between the chord connecting them and the plane P tends to 0 as P approaches. Is approaches double P or single P? Approaches P0. Do you see why this is not phrased in a very well-defined way? Because I said fix a point P, and then I'm saying let P approach P0, but never mind. Is the idea clear? Okay, do you see the geometry behind this? So this is the definition of a tangent plane, and if the surface is the graph of a function fxy, then it's the tangent plane to a point fxy. And do you see that somehow from this, having the phenomena of being differentiable with that star property and so on, it's not entirely trivial how to show that having a tangent plane in this sense and being differentiable in the sense of the definition that we had, why those two are an if and only if statement, that's not completely clear. Do you agree? Okay? And I'm not going to spend time on proving all these equivalences, but we will discuss various aspects. Okay, and also in homework you'll have. So for example, maybe I'll just say a couple more things, or maybe I'll write them. So equivalent definitions, this I won't write, but an equivalent definition, for example, a plane is tangent to a surface at a point P0 if and only if the plane contains the tangent line to any curve on the surface that goes through P0. Let me say that again. Take the point P0. Take any curve on the surface that goes through P0, any curve on my head that goes through this point. Okay? The tangent to that curve is going to be contained in the tangent plane. Clear? Okay, so that's an equivalent definition of a tangent plane. I just want to remark, so if the tangent plane to the graph of fxy at x0, y0 exists, if it exists, and we didn't prove it, but we know that if, for example, the function is C1 in a neighborhood, then it's going to have a tangent plane, then it's not a mystery plane, right? We know exactly what the plane is. We found the single candidate that it can be. Remember? We took the plane generated by the two lines with slopes, partial derivatives. Remember that? So then the plane is given, then, if the tangent plane P to the graph of fxy at x0, y0 exists, then P is given by z equals f at x0, y0 plus a, which was df to dx at x0, y0 times x minus x0 plus b, which was df to dy at x0, y0 times y minus y0. This is it. This is the tangent plane, if it exists. Clear? And this we proved. This we actually calculated, why this has to be the tangent plane, providing it exists. Okay? Okay, so I think this summarizes our kind of introduction to this notion of being differentiable in the two-variable sense. Okay? And where do we go on from here? That's going to be next time. Well, one thing we want to discuss is, for example, we had these partial derivatives which measured slopes in very specific directions, in the x direction and in the y direction, right? What if we want to go in the 45-degree angle direction? Okay, there's no reason not to want to do that. And that is a notion that also exists. It's called directional derivative. Okay, we want to discuss those. Then we want to discuss various properties of being differentiable and of taking derivatives. Like, for example, what does the chain rule look like for functions of several variables? Okay, so if the chain rule scared you in single variable calculus, please spend some time meditating so that you come into class calm next time. Okay, because otherwise you'll and then where we're going to go is some more general theorems, and a rather sophisticated machinery that will allow us to do things that we did in Calc 1. For example, find minima and maxima of functions. Remember how we did it in Calc 1? Set the derivative equal to 0, right? So there's going to be something very similar here to Fermat's theorem. That was Fermat's theorem. Okay, so how do we find minima and maxima, and how do we sort them? All that kind of discussion was closely related to derivatives, and we're going to have to build up towards that. Okay, so that's the end of this one.